complex backgrounds contained in the image, which are very hard to remove and which affect the accuracy of your algorithm. Also, when you are dealing with the infected leaves, in this case, the infection can deform the leaf in terms of its color and shape, such that you can no longer rely on color, shape, or texture features to classify accurately. In the last part F, we realized that there are also shadows which interfere with the perception of color from this image. Again, so you cannot use color features in such a scenario. So briefly, the general architecture of a convolutional neural network for classification is shown here in figure 3, whereby on the left, we input the image as it is captured by the camera. And then through a series of mathematical operations and sampling, we are able to automatically extract features from this image. And this is the part shown in yellow here. This becomes the feature vector, which is then classified to one of the classes to indicate which is the disease present in the image. So in this case, the extraction of features becomes automated, and the designer is relieved from that task of trying to design which features to work with. Also, the feature vector that is obtained is more robust and more descriptive, leading to a more accurate classification of the disease. So comparing the two approaches, we find that in deep learning methods versus the classical image processing methods, in the deep learning methods, the features are extracted automatically by the network, while in the earlier technique, the designer must identify and calculate the features manually. In the new system, one network can identify numerous diseases and pests categories in multiple crop species. Earlier, the shallow classifiers were limited to just a few categories, usually within just one crop species. The deep learning methods require large amounts of data to train the network. And the shallow classifiers can be trained using a relatively small amount of data. With the deep learning methods, the models take a very long time to train, usually hours, sometimes even up to weeks, to train just one model, whereas the shallow classifiers are trained within minutes. When it comes to inference speed, the deep learning methods are very fast. Inference here means the time taken to actually process the image when you want to classify the disease. So the inference speed is very fast with the deep learning methods, and the classical methods are relatively slower. The deep learning methods are more computationally intensive, thus requiring more powerful computers, especially for the training aspect. The classical methods have low computational complexity. The deep learning methods finally achieve a higher recognition accuracy and are also able to generalize better to images that they have not seen before compared to the classical methods, which we said are limited to very confined experimental setups. So for my work, the first part was to develop deep learning models for background subtraction from in-field leaf images using deep learning techniques. So the presence of the background interferes with the training of the model, leading to poor system performance. And also background features can mimic certain disease symptoms, leading to erroneous diagnosis of the disease. Previous attempts to solve the background subtraction problem had not been successful. Examples of methods that have been proposed earlier include the active shape models, graph cut, watershed, and soft computing techniques. So in many cases, with these earlier methods, user intervention was required in order to obtain acceptable segmentation results. In this case, the word segmentation means cutting out from the image the unwanted parts so that you remain with the parts that are of interest. So we proposed to use fully convolutional neural networks to remove complicated backgrounds from leaf images. So the advantages of the proposed models were that they were robust to hostile illumination conditions. They worked regardless of the orientation of the leaf at the time of image capture. I'm going to demonstrate this shortly. They were able to overcome color and shape distortion caused by leaf infection. No user intervention was required. And in the end, you obtained superior segmentation performance from the model. So generally, the structure of a semantic segmentation network is as shown in figure 3. The network only contains convolutional and pooling layers. So there are no classification layers in this case. So on the left here, you input the color image, and it is processed through the network. And at the end here on the right, you get the mask or pixel map to indicate this area of the image contains this particular kind of object. So for this particular study, the image contained 2 areas of interest. One was the leaf, which is what we are mainly interested in. And the rest of the image, which we are not interested in, was simply classified as the background. So the mask produced here in the output contained just 2 classes, the target leaf, and everything else was considered to be the background. So to facilitate the study, we assembled a data set of 1,408 images of tomato leaves captured under in-field conditions using various camera devices from 3 smallholder farms in Kenya. So both healthy and infected leaves were present in the dataset. And the images captured a wide range of illumination conditions. They also featured shadows, blurring, and a wide range of background elements such as mulch, human hands, and so on, stems, fruits, and so on. So no restrictions were placed with regard to the orientation of the target leaf in the image. As I said earlier, the deep learning methods require fairly large amounts of data. So hence the need to have around 1,400 images. We compared our deep learning method to the active Polygon model, which had been proposed some time back in 2013. So in that method, a polygon, roughly the shape of the leaf, was constructed and placed in the middle of the image, as shown in figure 4. And then we evolve the shape of this, the shape and size of this polygon until it approximately covers the leaf. So this evolution was done using the simulated annealing. So for example here, in the case of video 1, we have a more or less ideal scenario where the leaf is vertically oriented and there isn't too much clutter around the leaf. And we find that the polygon evolved and fairly accurately covered the leaf or demarcated the boundaries of the leaf. However, the shortcomings of this method were as shown here in video 2. If you have the same image, but now oriented differently, the polygon cannot evolve to match the shape and orientation of the target leaf. So the polygon becomes stuck in some local minimum and therefore not successful. Also, as shown in video 3, if the leaf contained deformations due to infection, then the polygon also gets stuck. It cannot evolve to cover the shape of the leaf. So this was a major shortcoming of this earlier method, the active polygon model. It could not work for leaves that were oriented in random directions, and also did not work for leaves that were severely deformed due to infection. We also compared deep learning method to the grab cut algorithm. The grab cut algorithm is an interactive algorithm whereby the user roughly demarcates the region of interest. In other words, you roughly encircle the target, and then from there, the algorithm evolves to segment the target from the rest of the image. So we compared two methods of demarcating the region of interest. One was using a bounding box, as shown in figure 5b, and the other was to give a more accurate approximation of the target leaf using a lasso. And we find from our result here that our deep learning methods, that is UNet and Segnet models, were able to achieve superior segmentation performance compared to the pre-existing techniques, both in terms of segmentation accuracy and also in terms of the speed of segmenting the image. So you find, for example, the active polygon model took on average around 94 seconds to segment an image, whereas UNet, deep learning network, could segment the images roughly in 42 milliseconds if the network was running on GPU, and in 1.3 seconds when the network was running on the computer CPU. Also, we note the consistency of performance of the deep learning model regardless of the orientation of the leaf. So in this first part here, the leaves were all rotated such that they were approximately vertically oriented. And in the second set here, the leaves were rotated into so that their orientation was random. And we find that the performance is very consistent regardless of the orientation of the leaf. With the active polygon, there's a big difference in terms of the performance depending on the orientation of the leaf. So this is a big advantage because it frees the user from having to orient his camera in a particular angle when taking the image. And also for future applications where you are going to implement this on, let's say, robots and so on, then they are not restricted. Qualitatively, we can see the performance of our networks, whereby for the first column, you have the input color image that is fed to the network. In the second column, we have the ground truth. In other words, what should the network give us if it is working correctly? It should have given us what is in the second column. In the third column, we have the actual output from the network, the UNet network. And we find that the output is a very good approximation of the actual ground truth what we would expect the network to give us. Similarly, Segnet also gave us a very good approximation of the ground truth, except for a few small errors such as this part here in the second row. But these are very minor, and this can be cleaned up using simple image processing techniques. We went further and enhanced the UNet network, which was the best performing network from the previous experiment. We enhanced the UNet network and formed a new network, which we called KijaniNet, whose performance was superior to both Segnet and UNet. In terms of the segmentation accuracy, we were measuring segmentation accuracy in terms of mean accuracy, mean weighted intersection over union, and mean boundary F1 score. So in terms of all these performance measures, KijaniNet was superior to the other networks. However, it was slightly slower than the other networks in terms of the inference speed. There's a question here from Damaris, which are the proposed? The proposed ones are here, KijaniNet was what we proposed for this study. Having determined that, coming back, that the deep learning methods were superior to the previously used methods, we then went ahead and improved on the pre-existing deep learning network to arrive at our own network, which is superior in terms of performance. So the main contributions of this study were that we proved that accurate automatic background removal for leaf images captured under field conditions was possible using fully convolutional neural networks. We demonstrated that semantic segmentation networks can be used to perform instance segmentation for exactly one instance of an object, provided that the target dominates the image, even if the image contains other similar but less prominent objects. In this case, even if the image contained other similar but less prominent leaves, those leaves were automatically pushed to the background, and we only took the dominant leaf from the image. Thirdly,
oh, sorry. Okay, thank you.
Thirdly, we proposed modifications to the encoder stages of the UNet model based on multi-scale feature extraction. The resulting model, which we named KijaniNet, outperformed all competitors in all three performance metrics. So how did we deal with the loss of data caused by pooling? Pooling gives you mostly because we are using max pooling throughout our network. So we take the maximum in a small region of the image and take that to be the representative of that section of the image. So inevitably, some of the other data is lost during pooling, but this is necessary in order to keep the computation costs of the network to a minimum. Otherwise, the network would become too computationally expensive to handle on the computer. So one way of dealing with this was to carry the lines in blue here, to carry some of this information across to the decoder, so that when now carrying out the decoding operation, we still benefit from earlier information obtained at the earlier stages of the network. And this way we are able to get accurate segmentation. So another question, computationally, what accounts for the improved performance of KijaniNet? Because of the multi-scale convolutions in the encoder stage, we are able to extract features at large and small scale at the same time. Gives you a better description of the features that are being extracted. So here it says CNNs are normally 2D, hence they fail to generalize well. They generalize quite well, provided that the data set you used was diverse enough. So for example, in this case, what we were using, out of the 1,408 images, we trained the network with about 1,000 images. And then the remainder, which had not been used to train the network, was what were used to test the network. So it was tested with images that it had not seen during training. And these are the results that we are reporting here. So the network generalized quite well. So next, we went a step further and now looked into the actual leaf itself and considered isolating the individual lesions from the infected leaf and then classifying these lesions individually. So most studies up to that point had focused on leaf disease recognition using images of whole leaf images. When classification is done based on whole leaf images, the CNNs may recognize the disease correctly, but based on some misleading features such as leaf vein patterns, leaf shape, and so on, due to the bias in the data set. So that when you now come to test the CNN with images where this bias is not present, then you find the performance of the network going down. Another limitation is that it is not possible to recognize multiple infections presenting on the same leaf from one image and one classifier. So it had been proposed to overcome this problem by performing disease recognition using images of individual lesions. That is, we segment the image to remove the background and also remove the healthy leaf tissue so that we are left with the infected leaf tissue. And then from this infected leaf tissue, we isolate the individual lesions and classify them one by one. So the advantages of performing leaf disease recognition from individual lesion is that, one, you have a great expansion in the data set, which is better for training the CNNs, because one leaf can contain, let's say, maybe 50, even up to 200 lesions. So when it comes to training the classifier, there's more data available to train that classifier. Secondly, the ability to recognize multiple anomalies on the same leaf using a single classifier. Thirdly, when you combine the lesion classification with accurate leaf image segmentation, it is possible to estimate leaf disease severity. So you can therefore be able to judge what is the stage of infection shown on the leaf. And then fourthly, if you do this over time, then you can be able to carry out analysis of the leaf disease progression. So this is useful for those people who are, for example, developing crop species that are immune to particular diseases or pests and so on. So they can be able to track how effective their work is over time. So to demonstrate this, we considered 5 scenarios. There's a question about image labeling. I'll answer this shortly. we considered 5 scenarios. One, shown here in A, figure A7A, is the basic image as captured by the camera. So simply take this image and classify using your disease recognition network or model. Or you can go one step further in B and remove the background so that you're only left with the infected leaf. Or you could instead cut out the rest of the image and only retain the part of the image that contains the leaf. So this is what we refer to as cropping the image tightly around the infected leaf or target leaf. Then in D, you can do both, remove the background and crop the image tightly around the leaf. And in part E, you could isolate the individual spots or lesions. And we find that from the results of the preliminary study here in table 3, we see that regardless of the classifier, whether it is a shallow classifier or a deep learning classifier such as Mobilenet, you attain higher recognition accuracy if you classify the individual lesions. We also note that, or we demonstrate here that the deep learning model has a superior recognition accuracy compared to the other shallow classifiers, the quadrature support vector machine, the linear discriminant analysis, the naive Bayes, or k-nearest neighbors. So this demonstrated that lesion classification gives us better accuracy for disease recognition. So how do we, for example, prepare this data for the background removal? We use the tool in MATLAB called image segmenter, and you can read the image and then mark the regions of interest so that you generate the ground truth masks, as I showed earlier in an earlier image. So for this study, we assembled a data set of 601 images collected from the internet. All of them were captured under field conditions and represented 5 crop species. And in total, 27 categories were represented in the data set, including healthy categories. So there are 5 categories for healthy, 1 for each crop species. And then the rest were for various infections. So the study had 2 aspects. One was the image segmentation. So given an input image, such as the one in figure A, to identify the 3 categories in the image, that is the background in black, the healthy leaf tissue here in gray, and then the infected spots in white. Then from these white spots, we go back to the original image and isolate them. This can be done in a software. So just calculate the connected components in figure B, and then cut those pixels out from figure A, and you are able to arrive at the individual lesions in figure C. So again, we compared our deep learning method, the KijaniNet proposed earlier. We modified it so that it now could segment 3 classes and compared against other methods that have been proposed for lesion segmentation, and we find that our method was far superior. Finally, we combined two networks to be able to classify the individual lesions. So first, we take the input image and segment the image into the three categories, that is background, healthy leaf tissue, and infected tissue. And then from the resulting mask or pixel map, we isolate the individual lesions here in the intermediate stage. And then these individual lesions are fed one by one to the classifier network, which we use Mobilenet for this purpose. And then Mobilenet makes a decision as to which infection is on that lesion. And in the post-processing stage, we labeled the RGB image. We labeled the RGB image as per the decision of the classifier. So this was the output from this model, that given the input color image, we segmented to get the pixel maps that are in the middle column here. From this pixel maps, we took the connected components, which are the white parts, and classified them one by one. And the network was able to tell us what disease was present in each of the spots. And this is what we find on the final column here. Finally, we went a step further and now looked at the efficiency of the CNN model for individual lesion recognition. And here we note that the models proposed earlier were quite large in terms of their memory requirement, in excess of 450 MB. And this is not suitable for applications in low power devices such as mobile phones or embedded circuits. So therefore, there's a need to downsize this model so that it can better fit into this application. So we extended the previous work by proposing a compact deep learning model for lesion recognition. We named this model Subnet. And this reduction in size was achieved by reusing the lesion classifier CNNs, the feature extraction layers, to be the encoder branch of the segmentation network. And then designed a custom decoder network to be able to perform the segmentation. The network made use of depth-wise separable convolutions, which normally reduce the size of the network by a factor of 9 or so. So the resulting model, which is Subnet, was more than 70% smaller than the competing models, yet performed better than those larger models. Here, the description of Subnet. Module A and B are Mobilenet, as proposed in the Mobilenet paper, Mobilenet version 2. And we use this network for classification of the individual lesions. But in order to perform segmentation, we cut out the classification layers from Mobilenet and instead only use the feature extraction layers with our custom decoder to perform the segmentation. And we see that for segmentation, Subnet performed better than the previous networks, but only at a very small occupation of memory. In terms of the qualitative output, we can see it here, comparing Subnet at the extreme right to Kijaninet in part E, UNet part D, Segnet part D, part C, and part B is the ground truth. And we find that both Kijaninet and Subnet are very good approximations of the ground truth, but Subnet becomes superior because of the lower storage and memory requirements. So in future, what are the next steps we would like to take? First is to continue to assemble larger image data sets for training more robust networks. And this is where collaboration with people in agriculture is very important, because these images, it's not simply a question of taking the images. The images need to be labeled by an agricultural expert who is conversant with crop diseases. So it's quite tedious and it's a lot of work. Next, we also need to extend these algorithms for applications in autonomous vehicles and drones. Third is to increase the speed of the lesion-wise disease recognition algorithm. You note that each lesion has to be categorized one at a time. And this can take quite a bit of time for leaves that have very many lesions. So there's a need to speed up that process. Fourth, which is tied to the second one, is to implement these algorithms on mobile applications and embedded devices. And then fifth is to continually develop more compact architectures using, for example, the current technology, the network architecture, such algorithms, to develop more compact and efficient models without sacrificing accuracy. So the work I've presented here resulted in 5 papers, one of which is still under review. And I'm very grateful to Egypt in Alexandria, Egypt, where I did this work, and to JICA for sponsoring my studies there, and Jomo Kenyatta for having given me the leave to go and study. So thank you so much also for your time. We take a few questions, I think.
Thank you very much, Daktari, for that very insightful presentation. I think there are some questions you've already responded to, but there is one from Zachary about that the approach appears to be very important in scoring disease severity, especially in different types of infection, multiple infections on the same foliage, and how it can be separated. I don't know whether you had addressed that. There's a question from Esther about did the reduced size of model affect the feature size during extraction process? And how did you undertake the image labeling for the images used in model training? You could also take it with this other one, the third one. Moving forward, I think this is now the next, what next? Is there an expectation that the improved KijaniNet will be available for use by plant disease diagnosticians? And what will be the terms and conditions of its availability? Have you patented this product?
No. Actually, I published the work, so it's out there, and I think in quite some detail, so it's quite easy to recreate.
Are you considering patenting it?
I'm currently looking at improving it first, and because what happened, KijaniNet could actually perform even better, but because of the limited computational resources that we had to downscale it in terms of its size. So okay. Now that I think a more powerful computer is available, I'll experiment with a larger version of KijaniNet and see how much better it performs.
Yeah, I think we can collaborate. There is a researcher currently trying to see the probability of having a HPC within the institution. So I think that will be of interest to you.
Yes.
Yes. Thank you. There's a question from Harun. Which classifier would you recommend for plant pathologists in the tropics?
I cannot recommend a particular one because the choice of classifier depends on quite a number of things. So for example, the first one, most importantly, is that you need the high classification accuracy. But then also you find this accuracy normally comes from the very big networks. And those big networks require more computational resources, which may not be available. So you pick the most accurate model that fits the resources that you have.
Okay, thank you very much. I don't know whether we have anyone from agriculture, the people who are actually in agriculture who might be interested in this. I had seen, I don't know whether they're here. Most of the people in the house I'm seeing are IT, ICT. But thank you very much for the questions. There's someone who is asking how they can access the data sets you collected from further research or experimentation. Would that be available for them?
The data sets are available. They can get in touch with me and I'll send them a link to the Google Drive where they are kept.
Okay, I think that was in response to, yes. Esther Mukoya is still not satisfied about your response about image labeling for the images you used in the model training.
Esther had a question about labeling.
The reduced size of the model affect the feature size during the extraction process.
No. The size of the network does not in any way relate to the number of features that you can extract from the network to a large extent, because first of all, we are using depthwise separable convolution. So the same network implemented using the normal convolution or layers would be maybe 9 times larger because of the parameters of that network. But when we reduce, we use the depthwise separable convolutions, the number of parameters reduces, but the number of features you are able to extract does not reduce. I hope I've answered, Esther.
I hope so too. Zachary has raised his hand. Zachary, you can unmute yourself.
Okay, thank you very much for this opportunity. Indeed, it's a very good presentation and questions have been responded to very well. I just want to make a follow-up on the issue of access and terms and conditions of availability. And for the response indicated that it is like a public good innovation, which might have its pros and cons. Now, if it is public good and is no patenting, it can easily be taken away and somebody can just do a small modification and patent it, and all your sweat will go to somebody else. That's maybe something you need to consider. We also would like to see the practical application so that we move away from the academics to practical application. If farmers would be able to share very high quality images from their farms with diagnosticians, they can get help. So in this case then, does it mean that now the farmers would just easily access it? And how easy is it for farmers to utilize this technology and be able to seek help from diagnosticians? That's why I was following up on the availability issue. Thank you.
Yes, the Daktari, kindly respond to that.
Okay, thank you. The availability of the data set for the time being is, in terms of the data, is available to anyone who requests for it. But the models and so on are not available. Also, I intend to further improve on these models because one of the main issues is that I trained them with limited data. Given that I was in a foreign country, obtaining the data was quite a challenge. So given the availability of more data locally and the development of more efficient versions of these models, then I think I can arrive at a more superior model that can now be patented. In terms of the practical applications, plans are underway to implement these models on a mobile application that can be downloaded and installed on smartphones. And there are two schools of thought in terms of how the farmers use these applications. As I said earlier, the models tend to be quite large. And when they're that large, it's difficult to implement them on the mobile device. So some people have recommended that we implement the algorithms or models on a web server. And then the farmers can take the pictures from on their phones and then send them to the server over the internet. The server carries out the diagnosis and then sends back a report. So the good thing is that the phone can then be a very basic phone. It doesn't have to be a powerful device. But then the farmer has to have a constant connection to the internet. The other option is to implement the model on the phone, make it compact, and then implement it on the phone so that except for the regular updates of the application, the app is readily available to the farmer on his phone. So we are still looking at both approaches and seeing how to go about it. The other application that I'm working on right now is to embed this on a small embedded computer, such that this can be, for example, mounted on a tractor or something like this, so that as other farm operations are continuing, then the crop disease surveillance can also be taking place in a passive way. So these are different routes that we can explore as we move forward.
Thank you very much for your response. We appreciate the importance of collaborations with various teams to make that happen. And through the Department of Research and Innovation, we are going to make sure that we give the platform for further collaboration among different fields, so that you can have that synergy to have an application that will be of use for many people. And Lusike Wasilwa is saying that maybe we could consider presenting more seminars, beginning with fundamentals to the high-tech level of presentation. I believe this is just a beginning on this field. And as Daktari has pointed out, there's so much further areas of research, and we are very grateful for that. Thank you. Our time has really flown past. Thank you so much, Daktari, for sharing your insights with us. And this knowledge is quite insightful and leaves us with what next. So wish you all the best as you take the next step of patenting and creating the apps to make it more, have a practical approach to your studies. Thank you very much for those who joined us late. My name is Dr. Rebecca Maina, and at Research and Innovation Department, we foster collaborations with other departments to bring you more of these webinars and public lectures. I want to acknowledge that our DVC RP was meant to be with us, but she's currently in a UMB meeting. Also in the meeting I want to acknowledge our incumbent Director Research, Dr. Kinyuru. Thank you so much for being part of us. And thank you very much for each one of you who made this happen. We really appreciate that you took your time to be with us today. Thank you very much. And with those few remarks, I also want to appreciate the department, the staff in the Department of Research and Innovation for helping us put this together. Thank you very much and have a blessed afternoon. Do you have a parting shot, Dr. Lawrence?
Yes, thank you. First, let me thank all who have attended this meeting and also for your questions. They are quite important in jogging the creative process so that can open up more ideas for future work. I hope to be able to link up with someone or people in agriculture. They are the most important part of this work in terms of labeling and preparing the data sets. We can, the technical part of training the network is relatively simple. The main work is in preparing the data. So that's where most of the collaboration is actually really needed. So thank you so much.
Thank you very much. And have a blessed afternoon. Asante sana.